So thanks for coming back again. So we'll continue to the discussion of Teichmueller dynamics and modular spaces. So last time, so let me first recall what we did last time. So I guess the most important part is the following thing. So we take a partition called mu. This is recall. A partition of 2G minus 2. So we define the following strata of abelian differentials H mu of follow holomorphic one forms consisting of pairs of a genus G Riemann surface X and a holomorphic one form omega, where X is genus G and omega is a holomorphic one form on X with the given number and multiplicity of zeros. So that is, so the zero locus of omega is sigma mi pi for distinct pi's in X. Right? So we introduced this notation and we explained several properties. So those properties, let me just briefly recollect. So this is not only a set, it has a dimension, it has a manifold structure using the period, and the complex dimension of this space is given by 2 times genus minus 1 plus the number of zeros n. That's one thing we showed. And another one, there is an important so GL2 action. Well, maybe before we do that, so this space. So we actually last time we spent quite a bit of time explaining the correspondence between a one form and the so-called translation structure, right? So this omega also corresponds to a translation surface structure X. So which gives you a very nice geometric way to think about a one form. So translation surface, we draw some picture before, right? Like this polygon and with edges identified. This kind of thing. So I showed you quite a few examples there. And once you have this identification, so just naturally by varying this plane polygon model of this one form, applying say 2x2 real matrix to this polygon that induces a global action called a GL2R action on the space H mu. Just by varying the shape. By varying the flat polygon corresponding to omega. Right? So we ended up with several concluding remarks and questions, including what we have known about the properties of these GL2R orbit closures. So today, so the focus is the most special orbit closures. So let me write down one definition. So before we do that, so let's also recall one more thing, that so the union of this H mu, or each H mu, admits a projection to the modular space of genus G Riemann surfaces by forgetting the one form and only remembering the complex structure X itself. So H mu admits a natural projection to the modular space of genus G Riemann surfaces. Is the space of genus G Riemann surfaces. And just by forgetting omega and only remembering x. That is a map. Okay. So in other words, so if you look at the projection, it forgets some information, but only memorizing the underlying complex structure, but forget the one form. Well, so one way to categorize the most special strata under this GL2R action is to look at the projection image into MG and consider the corresponding dimension of the projected image in MG. So let me make one definition. So from now on, when I say orbit, it just means an orbit under this GL action. If an orbit projection, so here projection refers to this projection to MG. So orbit lives here, right? Because this is where the action x. So you have some orbit going on here, and you project to the modular space of G curves. And if an orbit projection into to MG forms an algebraic curve, so this is rather special. Then we see that, or this orbit, or sometimes this orbit projection called the Teichmueller curve. So here, when I speak of Teichmueller curves, here curve actually means a complex curve. It's complex one dimension, real two dimension. So this curve actually means is a complex curve. Or in other words, this projection image, if this happens, actually also becomes a Riemann surface inside MG. It's complex one dimension. So, well, actually I have to say that this rarely happens because we also know last time I mentioned, so this action in general for the orbit, it goes ergodically around the modular space, right? Say suppose you take a general one form and take the general partition 1, 1, then this orbit goes ergodically around the Hodge bundle, which projection has to be also ergodically inside MG because Hodge bundle admits a dominant map to MG. In that case, in other words, if you take a general orbit and look at the projection to MG, there's no way to form a special subvariety, not mentioning to form an algebraic curve. So this is, if this happens, this orbit must be very special. And before I show you some example, so let me see that there's some other equivalent definitions for a Teichmueller curve, which is quite surprising if you did not know the context. So this is one definition from this flat geometric way and by looking at the orbit closure. So an equivalent definition, I won't explain. So this is just totally from a different viewpoint. So just as a remark, it's not relevant to our current lectures, but like this just suggests the rich geometry or the rich content behind Teichmueller curves. Another definition equivalently. A Teichmueller curve is a local isometry let me use C2. Local isometry from a Riemann surface C to the modular space MG. When I say local isometry, I have to explain what are the metrics on each side, right? So here you consider, put it this way. So this isometry actually is really coming from the, so here MG. So here the isometry, the metric I want to put on MG is Well, there's one special metric called Kobayashi, or currently Teichmueller metric. So here, actually, you take the universal curve of C, which in this case, if it happens to be a Teichmueller curve, it has to be the Poincare disk. You take the hyperbolic metric there. So this roughly tells you, using this definition, so a Teichmueller curve can be regarded as a sort of a complex geodesic under this Kobayashi or Teichmueller metric on the modular space of G Riemann surfaces. Yeah, I mean, indeed, I did not really know. Well, I sort of understand it, but I did not look into the details of the proof. But I feel like this is something interesting, and some other people in the audience may want to know this. Usually, when I work with Teichmueller curves, the way I think about it is usually from this flat geometric picture. Okay. So once we have this definition, the first, well, sorry, just one more remark, forgot. So this is one advertisement for maybe differential geometers in the audience. If you do number theory, here's another remark that might be interesting to you. So next one, so all Teichmueller curves are rigid over mg. So here the rigidity is in the sense of maps. That means if you have this local isometry, this map, as a map does not deform. You cannot find a non-trivial family of maps with this map as a central fiber. It's rigid. And for number theories, or for arithmetic geometers, so this rigidity really tells you. So in particular, so coming from this rigidity, Teichmueller curves are defined over number fields. For instance, you can define it over Q bar. Yes. So that means if you only look at these special orbits coming from Teichmueller curves, actually you can work with maybe not complex number field. You can find some strange maybe equations with some algebraic number as coefficient then to characterize this curve. Okay. And there are some research results going on along these circles of ideas. For instance, people try to understand for some special Teichmueller curve what is the minimum, also called the field of definition. And there are some results to characterize. Okay, so after these two remarks, so let's come back to some examples. So I have to convince you, so this definition actually is a useful one. In other words, it gives you some non-empty examples. At least there exist some Teichmueller curves. So there's one type of Teichmueller curves that people understand well, and we can cook up many examples out of this type. Here's an example. So this is rather special. They are called square tiled surfaces. So let me explain. Maybe let me make this more clear. This is Teichmueller curves generated by square tiled surfaces. In other words, I'll give you a very special one form whose flat or translation surface corresponds to a so-called square tiled surface, and the orbit of that translation surface gives you a Teichmueller curve. Well, so let's do the following setting. So let C to E be in a branch cover of the following type, satisfying so several conditions. So this is a branch cover between two Riemann surfaces. So C of genus G, okay, and connect it smooth, just a Riemann surface of genes G. And E, let's take it to be genes 1 and take the standard torus, the square torus, okay? It's genes 1. So let's take E to be the standard torus. This part does not really matter, I'll explain, but let's take the standard matter torus. So that's where first the square, this name square comes from. So you take a branch cover of a square torus. In other words, this branch covering curve C will be tiled by a number of copies of E to form a branch cover. Let's take this torus, and let's consider, give it a name, pi. Degree of pi is some positive integer d, fixed, some d, okay? And well, in order to describe a branch cover, we need to know the number of branch points, and over each branch point, what is the ramification info, right? So let's require only one branch point in E. So there exists a unique, so pi has a unique branch point in E. Only one branch point. So let's mark 1 point, because on a flat torus up to, elliptic curve translation, it doesn't matter which point you take. Let's take 1 point. Let's call it Q. All these vertices now becomes Q. Take this point in E, call it Q. And finally, so over Q, I have to tell you the ramification information. But I really want to cook up a translation surface somehow related to that special signature mu as a partition of 2D minus 2. I have to use that information. So over Q. So all the ramification points, now if they exist, they must be over Q, because Q is a unique branch point by assumption. Over Q, we require pi has exactly so where is my partition mu? I erase it. So let's take mu back again. M1 up to Mn. This is a partition of 2G minus 2. G is a genus. So I want over Q, pi has exactly n distinct ramification points. And each of them has ramification order given by the corresponding entry Mi. Let's call them P1 up to Pn, and each Pi has ramification order given by that fixed entry Mi in mu. Okay. So these are the conditions I impose to such a branch cover. So I told you the general of the domain curve and the target, genes G and genes 1, and the degree of the branch cover is pi, and require pi has a unique branch point downstairs in E denoted by Q, and over Q, pi has n ramification points denoted by P1 up to Pn in C, and each Pi has ramification order given by Mi. Mi is the ith entry in this partition mu. So this data is given, okay? So I want to look into such branch covers. So this looks still rather complicated. So let me even give you a sub-example. Just out of this branch cover, let me construct a concrete one. So let's take, well, say, suppose we let's take D equal to 5. The genus of C, let's take it to be 2. So let me take the partition mu. Now it's 2G minus 2 is 4. Let's take a single entry partition corresponding to a double 0. Okay? So I can really literally draw a branch cover using degree 5 means I need 5 copies of the square and glue them appropriately together to form a cover of E. So let's do it as follows. So we can construct the pi as follows. So here I have E, and mark it here. I need 5 copies. I do it this way.
This So you want this cover is cyclic or arbitrary?
Arbitrary so far. I haven't imposed any other, for instance, for the Galois group associated. No. If you impose those conditions, you get some more refined information. But so far, for the purpose to cook up a Teichmueller curve, this information is sufficient and necessary. But I'll come back to your question just after this example. Yeah. Okay, now it looks like 5 squares. Okay, 1, 2, 3, 4, 5. And I marked only some of the vertices on the boundary. So this one. And the other, these two, in the interior of the long edge, I leave it unmarked. And I have to tell you how to glue the edges together. Let's do it I should really use color chalk, but it doesn't matter. Let's do it like A, this is B, this long edge, and here's C, these two short vertical edges, and the last one is D and D. Okay, you should think this A goes to this A and identified under translation. So this long edge B goes to this B. And here C glues to C and D glues to D. Okay. And it does admit a cover to E just by literally take a point, look at the point in E. And this is 5 to 1, right? You have 1, 2, 3, 4, 5 copies. And you can check even on the boundary of this polygon and at the vertices after gluing, it forms a well-defined branch cover degree 5. And the genus you can work out using the topological Euler characteristic as we illustrated in the first lecture. So indeed, this example is still 1, 2, 3, 4, 5, 6, 7, 8 is an octagon. So it's only the shape looks different. This is really the example I showed you earlier to form a Jeans 2 surface with a double zero. So we have checked these conditions. And there is a unique branch point in E, that is the vertex here at Q. And for the interior point, apparently it's unramified. For take an interior point, you get 5 distinct pre-images. And the only thing we have to check is that this one gives us the right signature mu. We have to check there is a unique ramification point with ramification order equal to that case is 2. So I claim, so first, if you identify these 4 pairs of edges, the 8 vertices will be again glued to the same point. Let's call it P. Okay. And there are 2 other pre-images of Q sitting here, but this point is the same as that one because these 2 long edges are identified together. Let's mark this point by X, and the other 2 points, let's mark it by Y here, and this point is Y. Okay? Now, I claim if you look at the pre-image of Q, counting with multiplicity of the branch cover, you get X plus Y plus 3 copies of P. I mean, again, the way to see it, so pi is of degree 5. If you take the pre-image, counting with multiplicity, the total coefficient sum has to be equal to 5, right? And if you look at X, and you think if you move this B and just glue to B locally around X, you get a local isomorphism mapping to Q around X. And better way to think of in terms of translation structure is that around X, so here's angle pi, here's angle equal to pi, the sum is 2 pi. So whenever you see 2 pi, that means you only get 1 copy around the corresponding disk. Similarly for Y, so here's the angle is pi, here's the angle is pi, and these 2 glued together just get 2 pi and closed up. There's no other fuzzy issue. So for X, Y, just get 1 coefficient. That means locally this map pi at X and at Y, they are local isomorphism. However, at P, again, so the total angle at P, you just count, right? This is an octagon, so we know the total angle at P is 6 pi. That is 3 times 2 pi. And if you glue around P by this gluing pattern, you again see this like triple ramified covering setting locally around P, and you get 3 copies of 2 pi. That tells you over P, the total coefficient should be 3. But what does this mean, 3P? 3P just means that is, so the map pi, if you look at local neighborhood from P to Q, if you choose suitable coordinates, this 3 just means Z mapping to Z cube, right? If you choose coordinate. Well, I haven't really told you where the form comes from. But suppose here I have something like dz on E, and I'll pull it back. Maybe this is bad notation, let's call this is W. And if I have dW, I pull back dW. And if W behaves like locally at P and Q, Z cube, I differentiate and pull back in terms of Z, this becomes Z square dz, right? So remember what we said last time. If you have like integer module of 2 pi, the corresponding one form has vanishing order like a 1 smaller because you have to differentiate. Here, difference Z cube, you only get Z square. So that tells you, in terms of this translation surface, the corresponding one form really has a double zero at P. Tells. So the corresponding one form. And where this one form comes from, you just pull back dW from the flat torus. So here I have a nowhere vanishing one form. Has a double zero at P. So this double zero is exactly corresponding to the partition mu. Right. And every other point different from P is not a zero of this pullback one form. Okay. Right. So this example is called a square tiled surface, just because you see it is covered by square. It also has a, sometimes people also refer it to origami, I think. It's a Japanese word meaning folding papers. Yeah, so same thing. Okay. So here is an example of square tiled surface. So let me quickly get to the punchline. So why is it related to Teichmueller curves? So here at the end, I told you once you have this branch cover, so in general, you take the standard one form, say dW, on E, and pull it back. And just because of this ramification setting by the Riemann-Hurwitz formula associated to a branch cover, you know that the pullback one form, its zero locus is exactly of type mu, just by Riemann-Hurwitz, as you saw in this example. At least that gives you the one form sitting in the right stratum H mu. So let me get to the punchline. So in general, such pi induce a holomorphic one form by pulling back the standard one form dW from E. Let's tell you, maybe call it dW, this W, by setting omega equal to pi pullback dW, and just by Riemann-Hurwitz, and we know the zero divisor of omega in this case, just by the Riemann-Hurwitz formula, is exactly the ramification divisor. It really is a ramification divisor of the branch cover pi. So that is, by the setting of pi, pi has exactly n ramification points. Each of them has ramification order mi. So this part is just given by like m1 p1 plus mn pn. And now you do get one form of the desired signature. So it tells us, so this covering Riemann surface C along with omega sits inside the strata H mu we want. Okay. So this branch cover gives you one element inside the strata. Now I claim, now if you apply this GL2 action on this point and look at this orbit and orbit projection inside MG, you actually just get a complex one-dimensional algebraic curve sitting inside MG, which gives you a special Teichmueller curve. The reason is because now, so what can we vary in this case by this GL2? GL2 varies the shape of this thing, right? But look, if you vary this shape, because it is really tiled by squares, it is equivalent to varying the shape of E first, and then using the corresponding maybe not square, now parallelogram to tile your surface again. So the upshot now is that to varying C omega by this GL2 is exchangeable with varying the target torus structure first. And then look at the branch cover of this new E. So let me draw the picture to illustrate the idea. What do I mean by this exchangeable with E? That means suppose I have this branch cover. It's mapping to this E. Okay, I can apply GL2 on this guy, make it to any parallelogram you want, right? Maybe something like this. Let's make it. Okay. This is some GL2 action. And now I just take this as my new, not square, like a building block, 5 copies of it to glue this accordingly. That really means you will just see all the squares become of the new shape. But that's okay, just do it, get something like this. Right. So this is, again, a valid branch cover of the same topological type, the same degree, the same number of building blocks, and same gluing pattern, and the same ramification information. And there's an even better algebraic way to summarize what we are doing here. Varying E just means we consider all possible tori or all possible elliptic curves with any J invariant. That means we really look at this orbit now as a so-called Hurwitz space, which is a modular space parameterizing the corresponding branch covers. So what we did is that So there exists a complex one-dimensional Hurwitz space so let's call it H, D, G, mu, because it depends on these parameters, degree D, gens G, and ramification type. Parameterizing such pi satisfying that condition over any or every elliptic curve E. So here we require E can be, E can be any elliptic curve, not necessarily the square one. So in other words, just for people who are familiar with the Hurwitz space setting, i.e. this Hurwitz space so for any chosen E, so there is a so-called Hurwitz counting or monodromy problem which tells you over each given E, there are like only finite many non-isomorphic branch covers. Now you allow E to vary, so you can treat this Hurwitz space. So why is it one dimension? That I can explain. So you have this modular space of gens 1 curves. So along with one mark point corresponding to the branch point. So this is a modular space of all elliptic curves. So elliptic curve just means you have like an additional marking, right, Q. So it's a complex one-dimensional space, right, just governed by the J invariant. And for each point point here that is a pair E along with a marking standing for the branch point Q. And over it, you have like finite many non-isomorphic branch covers satisfying this condition of the desired type. And this finite many, this number is called a Pyrrhus number of branch covers, which in general is the number of branch covers when you specify the topological information of the base and the domain. That means you fix the general of the base domain, fix the degree, and fix the ramification point position and ramification information. Then it purely boils down to a monodromy question using symmetric groups. Like you go around the ramification branch point and look at the corresponding monodromy data in the symmetric group SD, where D is a degree, and try to find they satisfy all the relations in the fundamental group and try to compute how many are there. And that number up to isomorphism of branch covers is called the Pyrrhus number, which is always finite, in this case corresponding to this degree of this finite cover. And in particular, it tells us that this guy is also one-dimensional, the same dimension as the dimension of the modular space of real curves. And it is also algebraic because there is a general theory for Pyrrhus space of branch cover. You can just have an algebraic structure associated with it. Now what we conclude that this is also invariant now under this GL2 action because everything is already parameterized in the Pyrrhus space. And now whenever you have a square tiled surface, its orbit projection in the modular space MG is really the image of the Pyrrhus space in MG. But Pyrrhus space is just algebraic curve, in this case one dimension. So this gives us a special one-dimensional orbit projection which corresponds to a Teichmueller curve. So let me summarize. So in summary, in this case, this HDG sigma actually is a special example of a Teichmueller curve. Yeah, so there are like several things we really verified, proved. The first, so it is invariant under this GL2 because we will change the shape of E. So every branch cover is taken into account by this Pyrrhus space. By definition, this is the modular space of such datum over any possible elliptic curve. And secondly, just in general, we know Pyrrhus spaces are algebraic. So we have something algebraic. If you map to the modular space of curves, it remains to be algebraic. And this is one-dimensional in this case because it admits a finite morphism to M11. This is complex one-dimensional, and the fiber cardinality refers to the Pyrrhus number. So we have verified every requirement in the definition of being a Teichmueller curve. Any questions?
So this you can find this kind of covering, right?
That's a good question. So let me comment on this. So even without directly answering your question, so look, if you apply the Riemann-Pyrrhus formula to this branch cover, just because E is of genus 1, so 2 times its genus minus 2 is 0. That means this ramification condition does not impose any information to D, because that kills D if you plug in Riemann-Pyrrhus. On the contrast, if you consider a branch cover to the higher general curve, usually you will get some positive number times D that give you some only finite many choices for D. So this really means you can increase the values of D to get infinitely many, if they exist, infinitely many such Teichmueller curves. Right? Because there's no restriction imposed to D, right? At least in this setting you can take D as large as you want. Okay? If this branch cover exists, then increase D, you get infinitely many such Pyrrhus space. They are all different. Okay, so that tells you, well, you might be able to get at least heuristically infinite many Teichmueller curves of this type. Secondly, so you can do like two possible approaches to show given D, or at least when D is large enough, such broad cover exists. One possibility is to use directly this Horace-Kantian approach, but that's rather cumbersome because you have to play with like maybe even representation of symmetric groups SD when D is large enough. But there is a shortcut, which I sort of like just told Yungnan in person last week. So this square tiled surface, let me denote this square tiled surface here. So square tiled surface really are, if you think of them as one forms by pulling back dW from E, so these square tiled surfaces are so-called lattice point. In each strata H mu, if I see lattice point, I have to give you some coordinate, but we have a coordinate in H mu under the relative period coordinates. Okay. So let me try to explain. I think we have time, so let's slow down. And what do I mean by lattice point on the Pyrrhus? So maybe let me at least explain one direction. Suppose you give me such branch cover. How do I visualize the coordinates of that point inside the strata H mu under suitable period coordinates? So given, so let me explain this remark. So given pi C to E in that example is a squared tiled surface. Well, so what we can do is that, so what are periods? Period coordinates is, so the period coordinates of this guy, of the one form is pi pull back dW, right? Where dW is a standard nowhere vanishing one form on E. Now we pull it back. So this is the one we consider corresponding to the square tiled surface. Now we look at its period coordinates. So this one is given by just by integration of this one form along the chosen basis of the relative period. So gamma 1 W, and we have, remember we have 2G, absolute period without puncturing as a marking as a zeros, and we have additional G minus 1 relative periods. So these are absolute periods. And also we have additional, these additional periods are given by connecting like these special zeros to 1, 0. Let's take P1 connecting P2 and all the other P's to P1. So we have n zeros because the partition mu has n zeros, or equivalently there are n branch ramification points. Sorry. So these are called relative periods. Okay? Now we have this absolute period, relative periods. However, this one form is rather special. It's given by pulling back from E. Now when we integrate, we can push down, right? By push down. So this period is really equal to, let me write it here, all of them by pulling down. So these are gamma I. So now I get pi push down, gamma I, and evaluate d omega. Now I can transform these evaluations of this integration to the torus E, right? By the pullback push down formula. So for this absolute period, I get this. For the relevant, I can push down this path, right? I push down the path connecting P1 to Pi and integrate dW. Okay? Okay? Look, so each absolute period gamma I, they are already closed inside C. They are closed loops. So when I push down, to the standard torus and integrate dw, I just get some, like the real part and the imaginary part are both integers because I integrate along the closed path on the standard torus. Suppose it is like 1 times 1 square, okay? Similarly, just by the setting of the branch cover, although P1, Pi, they are different points in C, they all map to the same branch point Q. So this path is a non-closed path in C, but the image is closed in E. If I integrate, I'll still get integer real and integer imaginary parts. That's what I meant by lattice points. Conversely, actually, you can reverse this process. Suppose you give me a one form in the strata H mu under this period coordinate with integer real and negative coefficients. Then you can conversely to construct a branch cover using this information. It's not too hard. You can think about how to reverse it. Basically, you can integrate first, and there's some ambiguity. The ambiguity really comes from by modulo the period. But by modulo the period, if they have integer coefficients, integer values, then when you modulo this period, you just get the target will become like torus as a well-defined domain. It's not a standard complex number, but mod this z plus z. That tells you, given a special point in H mu with lattice coordinates under the period, you can conversely construct such a branch cover. So there's one possibility that this degree of the branch cover could be high. But that's okay. I'm not saying for each given D you have solutions, but if you consider all possible Ds, there are many of them. And so here under the period coordinates, the H mu locally looks like a cone. You have like period, and there's a lattice point. Every lattice point gives you a different Teichmueller curve. You certainly, by looking at like a larger and larger volume H mu, in other words, for D larger and larger, you will get infinitely many different square tau surfaces. This tells you they do exist, and they exist a lot, infinitely many of them. So this is sort of an indirect proof. Yeah, indeed. So this approach used by Eskin and Okonkov, just by evaluating this special branch covers, this Horst number, they try to use this information to compute the so-called volume of H mu, because they are lattice point. If you know the asymptotic growth of this number with D and with G, then you can compute the so-called the volume of each strata. Yeah, but that really boils down to some very hard combinatorics, especially representation theory of symmetric groups. But it was invoked by this idea, looking at the square tau surfaces as lattice point in the strata.
So then how could this GL2 acting on the lattice, how move the lattice?
Well, you can just look at well, that really means, so geometrically, the lattice point only corresponding to the branch cover to the standard torus. If you vary it, just means you consider, so each lattice point, if you vary it, it just generates the whole Teichmueller curve. In other words, if you have, suppose you vary it to this shape, you have to take this vector and that vector as your new lattice. So under this new lattice, you will still get lattice point. So here I mean lattice point for the squared, just means they have integer, like z plus I times z. But suppose you change it, so you just fix E of this type, just fix it, and consider this branch covers over this E. And there you will see, suppose this is V1, this is V2, you'll have this kind of two generators for your periods.
So then when you move this by action, then it contains the infinitely many lattice points, because you...
Well, I mean, when you vary it, for each orbit, I believe it only contains finite many, because each one, you should really think of it as just like a one-dimensional Hurwitz space over M11. So it is a finite morphism to M11. The cardinality or the degree of the branch of this map is given by the Hurwitz number, right? So for the chosen, every curve, there are only finite many non-isomorphic branch covers. This finite many, this number is called the Hurwitz number. This number depends on on D, G, and the ramification data are mu. For any given tuple, you'll get finitely many branch covers over any given E. So that actually corresponds to a specific orbit coming from like one lattice point there. Yeah, it might hit some other lattice point, but finitely many of them. So there's like one subtlety I did not touch because, so this way there's no guarantee that this Fourier space HDG mu is irreducible. In other words, more rigorously, this you have to start from here. If it becomes reducible, you take one component, and that gives you actually a Teichmueller curve. Otherwise, if you look at the project image to MG, it could be a union of several different Teichmueller curves. That also is related to what Yuna asked me earlier. So there's no guarantee. So if you impose this information, the Fourier space is connected. You might have to impose finer information, for instance, to the Galois group, or for instance, some cover becomes cyclic. This information certainly persists when you change it. So that certainly gives you at least one way to distinguish a possible connected component out of this total space. That actually is not easy to study. Even in GENS 2, classify the connected component of such one-dimensional Fourier space or Teichmueller curves was only done in GENS 2 by Kurt McMuller in the Annals paper like 10 years ago. Even for GENS 3, we don't know how to do it. It's just combinatorial, really very messy. Okay, let's see. Okay. Yeah, so let me just draw this concluding remark. So. First, so there exist other Teichmueller curves, not of type given by square tilde. Yeah. So in other words, besides this construction I told you, coming from this special branch cover, so people have discovered other Teichmueller curves, which are even more special, but not coming from this square tilde branch construction, or maybe not even coming from branch cover construction. However, so a complete classification of Teichmueller curve is still missing. It's unknown. So in low genus, we know some information, but in general, I think we don't have a complete list of Teichmueller curves. In other words, the complete list of special one forms that generate a Teichmueller curve. That we still don't know. And maybe let me just mention one known result. There are some other recent progress, but let me just mention one result. So in GENS 2, so Kelta and McMuller, I think this is both around year 2002, something like that. They classified Teichmueller curves in GENS 2. In other words, for GENS 2, we essentially know all possible types of Teichmueller curves. We can really write down the generating one forms. And in higher general, as I mentioned, so the complete picture is still missing. Okay, so we almost run out of time for the first lecture. So let me just quickly say what we are going to do in the final hour. So I'm going to introduce two quantities associated to, the first quantity actually is defined more general, associated to any GL2R orbit or orbit closure coming from certain counting problem on translation surfaces. The second quantity attached to a Teichmueller curve, or in general any one parameter family of GENS G curves. That is motivated by studying the intersection theory on the modular space of curves. after complexifying using the Dennett-Mumford space. So finally, I will show a relation between these two quantities and use it to exhibit some application. Let's see. Maybe let me just quickly start just writing down one motivation. So, and then we'll stop and take some break. So now I want to consider some counting problem on the translation surfaces. So let me quickly introduce the following object. So maybe so let's look at one example to illustrate this idea. So after this example, I will stop and we continue in an hour. One example. Let's count. So let's take a marked flat torus, so standard torus, say this one. E, I mark it at the origin. I suppose it's 1 by 1 size. Okay. And all these points are marked. Okay. Okay. I want to look at, now consider straight lines. So we have this flat torus. We always consider it with the standard Euclidean metric, just this straight line. Consider, we call it real geodesics, just straight lines on E. That, let's call this marked point, let's call it maybe P. That connect P to itself and have bounded length by some positive integer L, by some given positive integer L. Okay. And the question is, how many such geodesics are there? I really mean as really is asymptotic behavior as L goes to infinity. I mean asymptotically. In other words, I want to exhibit this answer such geodesics connecting P to itself on E with bounded length by L as a function of L, and look at the leading term. What is the asymptotics? Like, is it a polynomial of L? If it is, what is the degree? And what is the coefficient of the leading term? Okay, so I think I'll just leave it here, and it should be easy to figure out. So how about I'll resume next time, just starting from this question as a motivation. So let's stop here for the first hour.